presentation is by Mr. John Applewhite. Mr. John Applewhite-Hercules holds a bachelor's in civil engineering and geological engineering from the University of Guyana. He has a master's in mineral resources exploration from the University of Queensland, Australia, and he is formerly a trained teacher. Mr. Applewhite-Hercules has a strong interest in geophysical exploration and is currently the coordinator of the Guyana Mining School and Training Center, Inc. His paper today is about 3D modeling of lateritic paleo-surfaces using vertical time electromagnetics and DEM datasets in Mali, South Africa. So there's a sense of internationalism here, and I'm sure that there is a context for Guyana. Mr. John Applewhite.
Morning, everyone. Thank you, Mr. Dennison. This morning, I'm going to briefly present on a project that I was involved in for my studies at the University of Queensland. And it's using the airborne electromagnetics and the digital elevation model datasets, and using a combination of softwares to try and create a 3D model of the subsurface. And the objective was to create the 3D model of the subsurface so that you can be able to inspect the model and see if there's any structures that exist, structures that may be associated with some conductivity values, or if there is any potential for paleochannels existing in the subsurface. So I'm going to just give to you an overview of what I've done and the results. All right, so the introduction. This is the Google image of the project area in Mali, highlighted by those markers. The 4 points represent the extent of the project area. This area was mined extensively for gold. It's a known gold producing area. And I would now show you the geological composition of the area. Why we did the study. In this project area, there are some similarities to Guyana. West Africa and South America would have been connected in times past, and as such, they have similar geological conditions and similar tropical conditions. And we find that there was some dendritic or river-like structures in the land topography from the digital elevation model, and we were trying to investigate whether it was due to landscape inversion or whether it was some remnant paleochannels that was existing in the topography. So there are some terms that, to be quickly familiarized with. The glasses are basically different surfaces or height levels that exist, and you have about 3 main height levels. They're like a 350 to 325 height level, which is about 48 million years in age. There's a 325 to 300 level, which is about 27 to 29 million years. And there are actually 3 age dates for this level. So it's referred to as the middle and the lower glasses. Now this is a schematic of what the topography in West Africa is like. Like I said, there can be similarities in Guyana. Of course, I haven't done any follow-up to see the correlation in Guyana, but I know, for example, Mr. Bayer's company will have some information that can tell you of the manganese mineralization in the northwest and its relation to these different surfaces. So this is just a plot showing you the different heights and the ages that are present within the project area. A quick schematic of electrical resistivity of the area shows the various depths and how we can be able to identify it. Good. Now, why do we need to map these paleo-surfaces? I mean, the paleo-surfaces can be a target for several elements, including aluminum, iron, molybdenum, manganese, and so forth. And these elements are actually supergene enrichment, and they can be very good for discovery of gold. So we want to be able to identify these layers so as to identify them as prospecting targets. This is the gold content distribution in the profile. And we're now going to go into the actual study, which is looking at the topographic highlands. There's an observable dendritic pattern, and this may be due to some paleo channels, or that might be preserved due to landscape inversion. And further, we're trying to use a tool to model the subsurface or this paleo surface. So what we had was data set provided by two companies, Quantum and Resolute. They were able to provide a data set of this entire area. What you're looking at the surface is a grid up of the DEM data set, where the reds represent the highlands and the blues will represent the rivers. So you can actually see the river channels there. But if you also look at the yellow and red, you would see there's a kind of a river-like pattern, as if there are remnants of a river system there. So that is one of the things we wanted to investigate. The box in the upper left-hand corner is the data set and the 3D model that has been created. So there were some main objectives. We wanted to do a conductivity depth transformation of the geophysics data set and create what we call conductivity depth images. Also, we created a 3D model of the subsurface, and we wanted to examine the possibility for any paleo channels, or what was the relationship within the model to isosurfaces. And I'll give you a little bit more on the isosurface. So the methodology that was used, we combined an analysis of airborne electromagnetics, DEM, and other data sets, and we were able to map and create a 3D model of the subsurface, and we use this method to identify possible paleo channels and correlations with isosurfaces. There's a little bit of the geophysics involved. I want us to have a look at this slide because it's actually the software that actually was used. It's called Emacs Air. Allows you to process airborne electromagnetics and create conductivity, apparent conductivity results for each sample point. And it gives it for different depths within the model or within the earth. So after we would have run the software on the data set, this is what has been generated for the entire project area. And these are actual apparent conductivity results. So from airborne electromagnetism, we are now able to create apparent conductivity of the entire subsurface. After smoothing the data and doing some interpolation, we are able to get the data in a form like this. Now, we then use what are called isosurfaces, surfaces that are matching or connecting the same value of apparent conductivity. And so this isosurface that is shown in green here is actually collecting the apparent conductivity value of 10 microsiemens per meter. And the surface of the model is the DEM data set overlaid to show the correlation between the two. And This here is 9 microsiemens per meter, and its correlation with a DEM data set. And we note that wherever you see the isosurface spiking upwards in the model, it correlates nicely to the surface expression of the DEM. And therefore, there's a correlation that has been established between the DEM and what is happening with the conductivity at depth. And so we looked at 1 microsiemen increment at a time, 9, 10, 11, 12, and we examined. And then we also moved down the model, and we were able to identify from the apparent conductivity results, the reds are high conductivities, yellows, then greens, then blue being the lowest. And you would notice as you move into the model, this is 70 meters within the model. This is 80 meters down into the ground. And this is 215 meters at depth into the ground, into the model. What we note as you move from the surface, let's say from 60 meters going to 70, going to 80, then to 215, you see that there is now a splitting of the conductivity values. You're having like a zone of high conductivity values, which can possibly be due to some form of shear zone that is existing at that depth. So what we were able to do, we were able to have the isosurface again examined for depressions on the isosurface, because the isosurface being a surface that connects the same value of apparent conductivity, where there is higher conductivity values, it will be seen as depressions on that isosurface, because you're moving from low then to high. So to get a low, you have to go downwards. So by using the isosurface, you are able to graph the basement of any high conductive zones that's in the subsurface. And so if we consider what a paleo channel is, it's like a trench or a channel that will have materials that would not be as compacted as the surrounding material. And so you will tend to have a higher conductivity within a paleo channel. And so your isosurface can be able to capture that change in apparent conductivity. So what we're seeing here are actually remnants of possible remnants of paleo channels captured from the 19 microsiemens per meter. Here we show the correlation of those remnants in this isosurface. And we were able to conclude our studies by showing that whilst this technique or this method was applicable to Mali, which is West Africa, it's also applicable to Guyana because of the similar weathering conditions we experience. And it's also good to identify a way of picking up main structures that might be in the subsurface, whether it's a fault, a shear zone, possible remnants of paleo channels, and so forth. However, in Guyana, we do not have these large data sets that would have been available for the study. But what we do have and what we can access will be like ground electromagnetic data sets. So we can explore the possibility of utilizing or procuring a EM34 system, which will basically allow you to get ground electromagnetics. And you can do all that I've just presented there. So this can be good for identifying gravel layer, basement separation. It can be good for identifying stringers, as well as paleo channels that may be existing. So in summary, I would like to say that this method is relevant to Guyana, and with consideration and some training, we can be able to do this kind of work for miners at the medium and larger scale. All right, that's the end. Thank you. Any questions?
What's the depth of investigation of your tool?
Okay, so the model was able to go to a maximum of 500 meters into the ground. But of course, the Emacs Air software can give you results up to 1.5 kilometers. However, after you would have passed, let's say, about 700 to 800 meters into the model, the accuracy of the transformation it decreases. So good data can safely be gotten for 500 meters, and that is why my VOC set was at 500 meters depth.
So do you try to integrate surface geology with your data set to help ascertain the contribution for the...
Yes, actually, like I said, this study was done not just with DEM and airborne electromagnetics, but I also had access to the geology of the area and even some geochemical data that existed in the area. So we integrated all of this in SCORE in a 3D environment, and we were able to model and to see how well it correlates with what was there. So yeah, it has the potential to do that. So basically, SCORE GoCAD was this 2011 version was the software that was used, and just a little bit of training on that, we were able to create a model from the data set. Yeah.
How effective was this method in Mali in terms of the discovery? Secondly, when do you plan on applying this model to here in Guyana, and which area would you consider applying this model to?
Okay, so first question. This was a company that was actively involved in developing, they're doing exploration from a current mine. So they were exploring the vicinity of the Siama mine. The Siama mine has been producing millions of ounces of gold. So what they were trying to do was to identify more ore bodies within the area. So I was able to do the work as a student for them, part of it. However, I was not able to follow up to say, well, they had additional discovery. As a matter of fact, in my recommendations, I would have indicated that they should have investigated these remnants, these pocket-like structures that we saw on the isosurface, to do some groundwork to investigate whether there is something there. So I was not able to follow up on that. With respect to Guyana, however, I have done some preliminary works, and we see that the cost of an EM34 device, which is a strap-on kind of device with two loops at its two ends, will cost about $30,000 US. Its accessories will be another $7,000 to $10,000. And so you're talking about $40,000 to just get it done. And there's also a potential for this to create a kind of a framework with the University of Guyana and other technical persons who would want to evaluate their properties for these main structures. Where I would do it like in the Northwest, where there is not much coverage of our regional airborne mags. So that would be one of my priority areas that I would want to go and do it. All right. Any other questions? Thank you.
Okay, thank you very much, Mr. Applewhite-Hercules.